So my name is Andres, and both Marco and I work for Citus Data, and we are here to talk about how to get closer to doing real-time with analytics with PostgreSQL. And I'm going to start with a few explanations. And one of them is that all of you got some SSH keys. Has anybody not gotten one? No, sorry, IPs. The SSH password and username are up front, and we are going to, in the tutorial, going to reference a couple of exercises, and during those exercises you need access to the machines, and we suggest you do updated tutorial files, because I think we changed them since we created the virtual machines. So cd to the directory and do a git pull. You also can clone the repository yourself, and the slides are available on the top link. I'm going to leave that here for a second. It might be interesting to copy that down. So, okay. Just want to know what the next slide is, sorry. Yes, the Wi-Fi is PGConf SV, and the password is PostgreSQL with an uppercase P and an uppercase SQL. There's somebody at the end. Has everybody gotten Wi-Fi access, or anybody still has problems? So we are not immediately going to do too much with this, but if you can, while we're doing the initial things here, try to log in. And if you have a problem with that, raise your hand, and either of us will try to come by and help you. Generally, we will explain some things, and then every now and then we'll have an exercise, which will take you probably a while to run, to do, and then some of the exercises also take a while to run. And during that time, we'll continue and work here. So does anybody have problems logging in? Great. So we'll have a couple files in this PGConf SV tutorial directory. One of them is a loader script, which just loads some data. We're going to explain which data we're using and how to call this. And then that's the most important part. We have an exercises directory, and there's a couple files in there. We will reference the file names, and they will be for things that would take you too long to type yourself. You'll see when that is the case. And you can include these files because they are all SQL files using the psqls /i command, and that allows you to include another file, in that case, one of the files in exercises, and you can generally use tab completion. So you can write /i exercises tab, and it will autocomplete to the file name. Okay, I think with that I'm going to hand over.
Thank you. Still on? Yeah. Okay, so this tutorial is about real-time analytics. So what is that actually, or what do we mean by that? Well, on the one hand, you have a lot of cases where you have a real-time, or you have a stream of time series data coming in, like server logs or sensor logs, and or even transactional data, just the transactions in the system. And you want to do some analytics on this data. And preferably, if you, for example, are building a dashboard, you want this to be in real time, kind of in two ways. One is you want the user to be able to click things and it's fast. And then the other way is that you want this to get updated with the latest data as quickly as possible. So, but the combination of these two things with this high volume stream of data coming in and then actually doing these analytics as quickly as possible is actually quite hard. Because computing the aggregates over a very large data set of logs of something can take a very long time. Even in Postgres, we'll show you some examples where it will take several minutes to just do a very simple query on a large data set. Often you can use caching, but because you keep getting new data, you need to invalidate your cache very frequently, so you don't get that much benefit from it. So is there a way we can make it fast on both ends? That's what we're trying to answer. Can we have high volume data coming in and still have fast real-time analytics that gets frequently updated? So an example use case is when you're building a dashboard. Like the GitHub, this is an example showing the GitHub dashboard. I can maybe even show like the actual dashboard. So this is the Postgres GitHub dashboard. This is number of commits. And there's actually two different views here. One is per week, that's above here, and below is per day in that week. So these are the number of commits in this GitHub repository. And of course, most of this data is old, but in many cases, one thing is like when something happens, let's say today we want it to show up in this dashboard pretty quickly. And more or less, this is the use case that we're going to use as kind of a guide throughout the tutorial. So what we see a lot of companies do that need to build this type of dashboard is that, well, there's a few steps in your pipeline that you need to take care of. There's some events happening, things happening on your servers, for example, people clicking on things, clicking on ads, could be events. And all these events need to be collected somewhere and then stored in a database probably. Then we need to compute the aggregates over this data, and then we probably store the aggregates somewhere and then need to retrieve them. And what you see nowadays a lot is there's a big collection of different tools being used. Not specifically this one, but the common theme is that there's many different tools in the pipeline. So you might use Kafka to collect your events. You might use HDFS to store them. So you might use Spark to compute the aggregates over these events, the statistics, and then put them in Cassandra so your dashboard can look them up very quickly. So this is a very long pipeline, big operational burden. Now what we're going to show you that you can actually do most of these steps in Postgres. So you might have an architecture where there's just maybe some system for collecting the events, but then Postgres can store the data, compute the aggregates, and you can retrieve them from Postgres quickly. So one thing about like what are these aggregates we're talking about or views? So basically in these dashboards you often want to look at your data in different ways. Maybe you just want to see the number of things that happened, like number of visitors per day, or in case of GitHub, number of commits by repository. And actually, if we want to do commits, we probably need to break down by type, because there's different types of events that happen on GitHub. There's also an interesting one. What if you want to count something that's unique, like number of unique visitors in a day? So if the same one comes back, you don't want to count it again. These are typical views that you see in dashboards. And some of these can actually be derived from finer grained ones. So if you, for example, you have an aggregation per day, then you can derive an aggregation per week or per month from the aggregation per day. So we're going to use that later on. So what tends to happen if you try to use Postgres for this type of use case, just storing all your log data essentially in a table, and then you run a query like, okay, I want the number of events per type, so I group by type, count. That works great on the first day, but after a few days already, and especially if you start querying, let's say, over a month's time on this particular data set, queries start taking a very long time. You cannot build an application if you're around queries that take several minutes if you want the user to be able to interact with it. it might work for reporting applications, but not for interactive applications. And actually, if you're now connected to the EC2 instances, these you should be able to run queries like these. They will take a long time because we actually preloaded your databases with about 19 gigabytes of data, I think. So you'll probably be closer to the 2 minutes. So while everyone's waiting for their queries to finish, so in many cases you're not actually querying all the data. You're maybe just looking at the last month, but still lots of data sets. Just querying the last month or the last week takes a long time. So that doesn't necessarily make a difference. There's also what this picture is to some extent trying to show is that if you have these queries over kind of recent data, is that recent data is changing all the time, right? It's growing all the time on this end. So continuously, the result of this query will change, and that's part of the challenge. So the machines you're connected to, you have a database that is loaded with data from the GitHub archive. So whenever a user, every user-initiated event on GitHub is actually stored in this archive, at least the ones in public repositories. And the format is something like every line is a JSON object, and then it's compressed. And the JSON object describe an event. And there's a couple of different event types. There's like push event. I think everyone who uses GitHub would be familiar with that. You push commits into the repository. There's, start watching a repository, add a comment. Those are all very common events. So there's actually about 600,000 events per day in this archive, which amounts to about 1.6 gigabytes, very roughly. And one thing about this data set is that the rows are very wide. They're actually all big kind of JSON objects. I think in the next slide we should have, if you're start PSQL, you can see this data table which contains this data. And you don't have to run this command because the table was already created for you. But this is kind of the schema of the table. So there's some primary key, some GitHub ID type, that's the push event or watch event. Public, I suppose this is always true because it's only public data. Created at is when the event happened. Actor is a JSON object which describes the user. Repo is a JSON object that describes the repository. Org describes the organization. And then payload describes the event. And so payload is actually slightly different for every event. Well, actually very different for every event. And especially payload is very large. So these are all very large rows. So again, like this is actually the query that you've already seen. If you run a query like this, it's going to take, depending on whether things are cached, it might take 20 seconds, might take 60 seconds. It's a slow query. And so this is not a query that you typically want to run if you have a user that's clicking things and wants to, maybe the dashboard actually issues different types of queries where it looks at different date ranges, and you don't want to wait 30 seconds, 60 seconds every time. This is just, we added this because like the data uses JSON-B. Probably not everyone is familiar with JSON-B and how to query it. Now the main things to know are, and again these are queries that you can run in PSQL. Main thing to know is the arrow operator. So this is like column name, arrow, and then this is the name of the key in JSON. This selects an object from a JSON object. So you can have nested objects. But if you want to select a value like a number or a string, use the double arrow. Basically, otherwise you'll get back a JSON, your string as a JSON object, which is probably not what you want. So I'll leave it for a few seconds. We're gonna, we're not gonna heavily use the JSON-B, but we will sort of refer to, for example, the repository later on. So it might be useful to notice. And otherwise, you can find it in the documentation for Postgres. Okay, so we've added a little script on your machines to load data into the database. So you already have the first month of January 2015 loaded. So you could go into the PGConf SV directory. There's a loader.py script, which takes like the database name, or actually the DSN, and then a date range. Be careful, like if there's no help or documentation for this script, we kind of put it together pretty quickly. So just follow the exact format. Right. And you'll see this is actually per core. So per core, it'll load about 2,000, over 2,000 rows per second. And actually, most of the time there is spent just parsing the JSON in the input data. And this is, when you run the script, it's also like downloading it from the GitHub Archive website live. So we might now be DDoSing the GitHub Archive website. Did we cache February? Okay. We're not DDoSing the GitHub website. Okay, good. So we'll actually be using the loader script a couple of times, because we'll set up some things that happen when data goes into the database, and we'll see that some of those things might slow your ingestion down. You can make your queries quite fast, but your ingestion quite slow, but you want it to be fast on both ends. So this is kind of the baseline when there's no magic in the database yet. So it's about 2,000 or over 2,000 rows per second per core. So one feature, so how do we solve the problem of having queries that take 30 seconds? One feature that Postgres offers is the materialized view. So the materialized view is essentially just a cached query result in a table. So you can do so you run a query, put it in a materialized view essentially, and then you can do very fast queries on it. You can also create indexes on the materialized view. Now, the big drawback of using a materialized view for our purpose is that you cannot incrementally update them. You cannot do incremental computation. So there, after you create a materialized view, there is a command refresh materialized view, which will rerun the query. Like, when you create it, there's this select query over here, which is what you're going to cache, and this will rerun that query with the latest data. But that will take some time. One thing to note is if you're doing a refresh materialized view, there's this keyword concurrently, and this is quite important. If you do not use concurrently, you will be locking your view basically, and you cannot have other queries. So always use concurrently if you use refresh materialized view. So basically, when we have the materialized view, our query goes from taking 30 seconds to taking half a millisecond, basically. Because now also the query we're doing on the view is very simple. We don't need to do a group by anymore in the view. We already did that at the start. I'll show you the query I'll show you what we put in the materialized view in the next slide. Might be in the wrong order, but the problem with the materialized view is essentially this step is very big and very costly and very slow. So this is the command that you could use in PSQL to create the materialized view. So so we're going to create a view that's called data daily counts view, which will be able to query almost as if it was a table. So created at was the field which said when the event happened. We're kind of going to cast it to a date, so we're extracting the date. And then we're also grouping by the date. So this will give us the number of events in the GitHub dataset for each day of January, essentially. And as you can see, this can take quite a while. So have patience. But in general, like when you, whatever, all the methodologies we're going to discuss are, this is the problem of, well, you already have a bunch of data, and now I want to compute aggregates for all that data. And that step is always going to take some time. The problem with Materialized View is that adding new data, again, takes this much time, and this is not ideal. So once you've created the view, you're able to query it just by doing a select star from view. You don't even really need to do this filtering because, you know, this is basically just all the data that's currently in there. You probably want to order by created date because, you know, if we're using this to draw a graph, then, you know, we want the dates to appear in order. And you'll see this query is really fast. I imagine most of you are still waiting for your Materialized View to create, but I'll show you how to actually refresh it. So we're going to use refresh Materialized View concurrently. One thing you need to do to be able to do the concurrently part, which is essential, is to actually create a unique index on the date, or the refresh Materialized View code wants there to be a unique index. Now, in general, creating an index on your views, on your aggregation tables, is probably a good idea. Like in this case, you know, the month of January only has 30 days, so it's not very interesting to have an index on 30 days. But later on, we'll show you, well, what happens if you group by date and event type and repository, and then suddenly you have a pretty large number of rows in your view. So in that case, you probably really want an index for the queries coming in from your dashboard, like that one, to be very fast. So the problem we're facing here is that, well, hopefully most of you have managed to create the Materialized View and might be getting to the refresh Materialized View. But again, the refresh Materialized View takes about as long as the original creation, sometimes even longer. And by the time our view is updated and we see the new data that has come in, basically we're already behind. Now, I think in this data set, it's not too bad, or in this setup. So you'll get a minute behind, which might be okay. In many cases, it's not okay. And in many cases, you have more data, more than 600,000 events per day. And you will simply not be able to keep up with your ingestion. So it works well if you have a moderate amount of data, and it's okay to actually do periodic background refreshes. You do not need to keep up to date with all the latest data coming in. But it doesn't work so well if, in general, you have a very large data set, so you cannot, like, it just takes too much time to actually compute these aggregations, which is too costly. If you have a very high rate of ingestion, you won't be able to keep up. And if you really need near real-time views in your dashboard, you basically cannot use this. So now Andres is going to solve that.
So one thing here to mention is that some database management systems actually can do materialized views that are automatically incrementally updatable, but Postgres, to this date at least, can't do that. So what we are trying to do in the next steps is to get to the point that we can build a framework ourselves to incrementally update a few type of views. Obviously, there will be a lot of restrictions, but it shows the general approach how to do that. And maybe someday, some people will actually implement this fully in Postgres, which will be nice because it means less work for us. But right now, that is what you can do. So generally, the approach here is that we want to pre-compute data and store that data somewhere, and that we want to, in small steps, keep the data up to date. And generally, the approach in old school relational database management systems is to use triggers to do actions on write. So the absolute most simplistic way we can do this for the simple data count daily table that we have created earlier would be to, on every insert into the data table, we update the count in the data count daily tab, because then it will always be up to date. So let's try that, because that will be the most simple approach, and that's, if simple is good enough, why do something more complicated? We'll see whether simple is good enough. So let's create the table that will contain the counts. So that's just, again, create table data table counts cached. And it has created date as a primary key, because the primary key is the date, because we want to have one count per day. So that's pretty simple. And for now, we're just going to say we store the value in there, and that's going to be an integer. And because we want there to be initial content in that table, we want to not only maintain it going forward, but we will also want the initial content to be correct. We are going to insert into the table using a simple insert statement that basically runs the query that we ran earlier before and inserts all the resulting rows. So, and then the next step from here on is trying to keep that view up to date, or create that materialized view that we created here up to date whenever there's modifications to the data table. So we earlier said that there sometimes are going to be exercises where it's too much to type for you. We don't want you to have to type all this. There's a file here which contains this. You can actually, once your script has run, use this with /i path to the file to actually execute the trigger. But so what we are trying to do in that trigger is basically whenever there's an update, or whenever there's an insert, we want the trigger is going to be run, and then we are just going to say we update the cached table of counts and set the value equals the value plus 1. That's pretty simple for a count star. You just need to, every time a new row comes in, you increment the count. And we do that by date, because we want the daily count. But obviously, when you start a new day, that row in the table might not yet be there, because we started a new day, there has not been any previous row. So we have to check whether that row was there. If the row was there and we updated it with +1, we're just done. That's simple. But if not, we have to insert the row, and that's what we're going to do here. We'll insert the row into the cache table with the created add of the row and a 1, because it's the first row. But there's a big problem here. If you do this from several connections at the same time, between up here and here, somebody else might have inserted the row, and you might be in a transaction which can't yet see the row that's inserted in a concurrent transaction. So we have to handle the case where somebody else inserted the row, and in that case you will get a unique violation, because we had the primary key, and the primary key is defined to be unique. So you will get the error. In that case, we'll just loop around and try again. Since now the new row exists, we should be able to update it now. So by now, this here just created the function that we want to run in the trigger, but we also have to declare that there's a trigger on the table. So what we're going to do is to just say create trigger and some name. After every insert, which is important, we're just going to handle insert in this simple example. We want to, for each row that is was inserted, we want to execute this function that we just declared. And that's also already done as part of this update daily aggregates SQL. So now we have added code that maintains this table. What we have to do now is to actually see how bad is this for the loading throughput. It might be that this is really good enough. But so let's try that. We are going to load another day of data here. And because we'll see why, we are only loading a day in a second. So we run the loader script again. We have to be in the PGConf tutorial, SV tutorial directory for that. And we run it for 1 day. And you can see that even for the first worker that finishes, like the first process that does the insert finishes, it only does 380 rows, where we were around 2,000 earlier. And you can see that every further insert or further process that processed one file here is getting slower. So you're probably not going to be able to finish this, or you don't want to wait till it's finished. So once you're satisfied that it's too slow, just press Control-C, and that will stop the script. It will take a while for the script to stop, because it will try to finish inserting the rows that the files it started processing. But just press Control-C. Yes?
The loader script normally actually uses all the cores to insert data, but as you can see, actually only one core is busy in this case, because actually they're all locking on on the same rows. So one of them got pretty good performance, and the other ones are all being starved, as you say.
Can you switch back to the slides? Or Control-C, it will continue in back. Okay. So why is this so slow? If you look at the trigger that function we declared, there's two major issues why this approach isn't really suitable. This one annotation here, to understand this a bit better, each of these imports here of one file do process 1 hour of data, and 1 hour of data is always done in one transaction. So it's basically a bulk import of a couple thousand rows. I mean, what is it? 15,000 rows at once or something. So each of those are one transaction. And if you look at the update statement, what you do is for each row, we update one row here, and we say the where clause for that is where created date is equals new created date. What that means is that if we insert several rows for the same date, all of them have to update the same row in the cache table, right? Because all of them happened at the same date, or happened in the same few days, which means all of them will block on the row level lock in Postgres. Because in Postgres, or in most relational database systems, only one transaction can update a row at a time. So what will happen is that the first the loader that starts for the day, that loads something for the day, will update the row, and then all the other workers will have to wait till that day has finished, that loader has finished, because it will block there. And then the second one runs and also waits for the rest. So basically what you're doing when you do a materialized view in this way is you're blocking on so that only one process can update something at a time. That's really not suitable, because we have multi-core systems. You can't usually keep up anymore with a single process. There's a second problem, which is that at the moment, for each insert into the source table, we do an update of the data daily counts table, which means there will be very, very many updates to that table. The higher your ingest rate is, the more updates of that you will get, and that means that table will get very large. Because in Postgres, every time, or in some other databases as well, every time you do an update, you mark the old version of the row as dead and insert a new version of the row which contains the new values, which means there will be many, many dead rows, which explains why things get even slower after the first batch of work is finished. So we can see that this approach really isn't suitable. You can't just create a simple trigger that updates your aggregated table and maintains it that way. It works sometimes. You can actually make this work if you have an aggregate which is very granular. Say if you had instead an aggregate which computed something per repository and per event type and per day, then there wouldn't be that many events, because usually, for example, in the GitHub data, you will not have thousands of commits per second for the same repository on the same day. So then in those cases, you can get something away with doing something as simple as this. It's also worthwhile to note that this whole loop around the update here and the insert with the exception handling isn't necessary in 9.5, because 9.5 finally has upsert, and you can do this whole body in one statement. So one approach to solving this problem is that we can say, hey, since we only do inserts in our simplistic example, we can say every time a date is finished, we compute it, and only the data that's basically still changing in our aggregate gets updated, or we recompute it every time. So querying the old data, which is in our cache table, as fast because we pre-computed it. But the new data, which is currently still evolving, we query the source data and recompute the aggregate. That is an approach that sometimes works quite well. So you might want to consider doing that. Just query the most recent data and cache all computations that are older. The case where that doesn't work at all is if you actually modify older data, or if your aggregate isn't over time. If you, for example, wanted to compute the number of commits as a total in per repository, you couldn't do something like that, because each value in each aggregation result will change over time. So that's sometimes an approach, but it's not really suitable for the generic case. So to solve this problem with the locking, a simple approach is, or the next trick is to say, instead of updating the row, we have a queue of updates that are made to the table. So we don't just have the daily counts table, we also have a queue that schedules updates to that daily counts table. And every time somebody inserts into the data table, we say, okay, the daily counts table now has to be updated, and it's for the 17th of November, and we just added a row, so the count has to be increased by 1. So we insert into the queue a 1, but we don't directly modify the materialized view. If somebody deletes, we do the same. We just we insert a -1 because the value for that day decreased by 1. If somebody updates, we say delete for the old date and insert for the new date by 1. If you can optimize this, obviously, by saying, I don't need to do anything if none of the relevant fields changed or something. But that's basically just making it a bit better, micro-optimization. And I guess you can easily think of ways how we can do this approach and handle more complex aggregates. If you want to, instead of, say, count, you want to do sum of something, you just don't insert 1, but the actual value. If you delete it, you insert the minus the actual value, and so on. There's approaches to how to do different types of aggregates here. Not everything is easily possible or efficiently possible that way. But it works for many things. So, but if we just, we have this queue now, but we want to have real-time view of the data. So what you need to do is we need to combine the state that is in the materialized table and combine that with the changes that are pending in the queue. So what you do is we create a view that queries both the materialized table. That's what we do here. We query the select created date value from the cache table. That will just be a normal query over the data table. There's only 1 row per date, so that's pretty fast. And then we do a union all with the rows in our queue. And what that means, we look at all the pending entries in the queue, and then we just group by the result again. And what that means is that we take the initial value in that we already computed. Say we already had 211 for the 17th, and then we see we get another row where it says +1. We get another row where it says -1, and then you do another group by, and then we'll say, okay, the group by for the sum of 211 +1 -1 is again 211 in this case, so it's easy. The result hasn't changed. Doing this, if the queue size isn't too large, can still be very, very fast, because you only have to update, compute like one row for here, the 17th, and then all the pending entries. But obviously, at some point, your queue is going to be too large. You have to do something to shrink the queue again and update the materialized value. Do you want to show that, or? Yes. I think you can go back. So what you now need to do is to add a trigger that inserts these queued events into the queue table, and that's not that difficult. We just have to write a trigger that, like we did before, it will be called whenever there's an table into the data table, insert into the data table. What happens is we say, was the operation an insert? If the operation was an insert, what we do is we insert into the queue the created date to the created date column, into the difference column, the value date chunk, day, and created at. That's just another way to specify how to truncate the created at to a date. And then we say +1. And obviously in the other cases, for update we do the +1 and the -1 and the +1, and for the delete the -1. And what's then interesting is that after that, every now and then we want to flush the queue, because if it gets too large, things get slow. So what the simplistic approach we chose here is to say every 10,000 rows, approximately we want to flush the queue, and you don't want that to be like actually every 10,000 or something, because that will lead to that happen in all inserts, all backends at the same time, which is not good. So it's a probabilistic thing. Every now and then, just flush the queue. If it takes a bit long, if we hit an unlucky streak and it takes 50,000 rows, so what? It's a bit slower. And again, the file to create this function and the trigger is in here. So the more interesting part is how can we then use the queue to update the materialized value, because that's what we're pretty much desiring to do. The trick here is to use so-called CTEs, which is a common table expression, which in those you can do multiple DML statements, statements that modify the database in one large statement. So what you do is we first compute all the final values of the in the queue. At the moment we most likely have like 1,000 or 10,000 queued updates to one day. So we want to compact those. That's what we do here. We're going to look into the details of each query in a second. Then we want to know whether there's already a value in the materialized table. That's what the pre-exist does. And then we want to update all the values in the materialized table that already exist, insert the ones that don't exist, and after that we can finally just delete all the entries that are in the queue, because now we've applied the updates, the pending updates to the table. So we just call all the perform updates, perform insert, perform prune, and that will run these queries that are nested in each other. And we can, for example, log the output of that into the server log or anything. No, we couldn't, because truncate takes an exclusive lock, and that would mean that any concurrent reader would block on the wait. Doing the delete means that anybody else that is currently reading from this union between the materialized table and the queue table can still continue without being blocked. So that's something you don't normally want to do. It's a plain table, because you're not allowed to update materialized tables. So that's why it is one. It would be nice if all of that would be possible within the framework of materialized tables at Postgres, but we're not there yet. So looking at the individual steps, what we do with aggregated queue step, we just go over the queue and do the group by there. The reason we do that in the queue is that then the further step will have to deal with many, many fewer rows. Because usually, if you do something like by created date, you won't have more than, I don't know, 20, 50 days that have been changed. And then we need to check whether these rows already exist in the materialized table. And for that we use an exists semi-join. We check in the data daily counts cache table whether a row with materialized created date already exists. And the result is a column that is named does exist. This here, we should maybe have changed that. There's an as here. That's just an alias for the column, because otherwise it's going to be named question mark, column question mark, and that didn't seem very descriptive. And the star here is so that we have all the aggregated rows from the queue. With that, so now we know which rows are already in the materialized table and which are not. So we can say, update all the rows in the materialized table, set the value for the existing value plus all the changes that have been pending, and do so from the row that we have from this table here, and only update the ones where we know that they exist. And obviously also have a join between on the date, which is our aggregation value. And we return 1, so we can easily do a count star. But we don't really need any other values. For the insert, we do exactly the same, except that we do an insert and obviously say where not exists already. The pruning is pretty obvious. As asked before, we have to use a delete here and not a truncate, because the truncate would require an access exclusive lock. And by that, we are pretty much done. So if somebody of you paid a lot of attention, they might have noticed that we have the same problem in this step here in the pre-exist one as before in the trigger. There's no guarantee that we see the rows that have been concurrently inserted by another transaction. So we have to make sure that the flushing process only runs in one backend. Then we have a lot of easier. So to our flushing function, we add we have to make sure that it only runs in one backend or in one session. And if it can't if there's others running, it should just return without doing anything. So Postgres has advisory logs for that purpose, which is just logs that you can say log on some integer value, and if somebody else has already gotten that, we'll get a false back. That's why we use pgtry advisory log, and then we'll get a false and just say, okay, we can't currently flush the queue. If we get it, we get a true back and continue. If you instead used pg advisory exec log, then it would wait for the log to be free, but that's not what we want here. We don't want to delay an insert that is doing the queue flush to be delayed till somebody else finished. So, and if we got that log, we just continue with that long query that we had before. So as a final thing, we have to create the trigger again on the table that for each row, but this time after an insert or an update or a delete, because our trigger now handles all these, we execute the function again. So let me switch. So now we want something that a query. Can you go back to the slides? So now we also need the view that returns this. That's basically what we showed off before. It looks at the cached materialized view or our own created materialized view and the queue and returns results. And we hope that this now is pretty fast because we basically pre-computed everything. And as you can see, in this arbitrary example, if you do it now without any time qualification for the 1 month view we had loaded, it only takes below 1 millisecond, which is pretty good. If you're these times here will vary a bit because depending on whether your view was like your queue is empty or your queue is pretty full, you need to do more or less work. Yeah. So, by the way, this is the file that creates the view. So, and the important part is where we now measure our success is whether the loading now is actually faster. But because if we did all of this to have no benefit, then we would have wasted our time. So, but luckily, given that we're here, it actually works to some degree, and we can get now around 1,900 to 1,700 rows per second, and that 1700 one is likely the one that had to do the queue flush, because obviously that's going to slow you down for a short while. One of the files previously dropped the trigger for the old approach, So if you manually created all the triggers, which I think is rather unlikely, then you need to drop the old trigger to the old approach, because otherwise the old approach obviously will block us. Like, be the bottleneck. Like, perhaps here? What's happening here? Oh no. Oh, that's not what you want to see? Oh yeah, for some reason there's one file in the GitHub, an hour in GitHub where only one event was happening. I don't really know why, but whatever. Okay. I don't know how to switch back on it. I have no idea how to use Mac, so that's why he has to run the exercises, and because it's his laptop and I don't dare to touch it. It could burn my hands or something. So we basically, oh, could you show the we could just import. I think it's fine. /dt plus. So now in this example, can see that our data is at the moment 22 gigabytes, and our materialized view of the data is 3 megabytes large, and the queue is 24 megabytes large. So we can see that we're dealing with the changing parts of the table that we materialized are pretty small, which is exactly what we want. We don't want to continuously work with gigabytes of data. So, but what if you don't actually just want to group by something like the day, or because you're interested in hourly events, you're interested in daily events, you're interested in monthly events, which is pretty common. You normally want to look at the highest level view, for example, the rows over a whole year, like the progress over a whole year, and then you want to drill down, oh, here's something strange happened, I want to look into this, or this looks cool, and I want to see what happened there. Why was there more happening on this weekend, or something like that? So what you often want is not to just do the daily or something. You want to do first, for example, in our example, you want to have an hourly overview because you have lots of events per hour. Then you want to have a daily overview and then a monthly one. It's not that often useful to actually roll up higher than a daily view, a monthly view, because there are just not that many months in a year, and you don't usually operate with that many years. So, but if you want to do yearly afterwards, whatever. So we can basically do the approach that we have used before. We can first do, using the method we had, do hourly aggregates, and by using the queue trick, we insert into the queue, then compute it, and we then can say, now we want to also update daily aggregates, but we don't want to, for the daily aggregates, we don't want to recompute everything we did for the hourly ones, because that would be a waste of time. We don't want to have to process for the monthly granularity 100 million rows or something, I don't know, okay, so 14 million rows for a month, if we instead could just fall back to the 30 days we have already computed, because 40 million and 30 days is obviously a pretty big difference. So what you can do is, whenever we insert into the materialized table, whenever we have flushed the queue, we can use the hourly events and log the change to the hourly events into the daily queue, into the queue of the next granularity. So if we change the materialized table for the hourly, we can then use the change, and insert the change into the queue for daily. If we have computed the actual value for the daily one, we can go ahead again and insert something into the monthly queue, which means that for monthly we usually will have to only do very few changes, because we won't flush the daily queue all that often. And in return the same. In comparison, we'll update the daily queue much less frequently than the hourly one. But if we have to do all this work for each granularity, manually create triggers, manually set up queue tables, that's going to be a lot of work. So at this stage, you probably want to automate this a bit, because it's not really feasible that everyone in your team has to write lots of PGSQL or in whatever language that you write this. So what we did is basically write a script to automate this for very few common cases. It's obviously not a generic materialized view approach, because then we would have just submitted it to Postgres. But I think it's an approach that I've personally used in the past in production to set up lots of materialized views, and it's relatively easy to extend to further use cases. You might find that the code isn't super pretty. So what we have is we want to set up these cascades of tables where we say we want to roll up, for example, the table data, and we want to say we want to group by, generally we want to separate the different types of events, because usually we are not necessarily that interested in how many people commented on issues or something like that at GitHub. We want to look at that separately, because the number of issues might indicate something entirely different than the number of commits, because that they might be inversely correlated in some way. So what we say is here, the table of the name we give this rollup is data by type, and we want to group by type, and then additionally we want to have several aggregation steps. For example, we want to say we want to look at the hourly aggregates, we want to look at the daily aggregates, and we want to look at the monthly aggregates. And we give each of these steps the name hourly, daily, monthly, because we want to have some descriptive name. And it's important here that the script as written only works if the finest grained granularity is up here and then goes to less granular from there on. And we want to name the column that contains the this value here, we name it created at, whatever. And what we want to actually compute is count star, and we want to compute the count star, we want to save that in the count star column. And that's, again, because way too long to type, saved in this file. It's going to take a couple seconds to actually run this, so let's start. You can see that it here says, okay, I'm starting to fill the materialized table with all the pre-existing data. So what it now has to do is to insert into the tables it creates all the pre-existing rows, which will obviously take a while because it now has to do the whole group by created date by order truncated to the hour, because that's the most fine-grained level we have here. So if you run into an error with this, I'm sorry, yeah, very good observation. This function is defined in the createAgg.sql. That's in the root, not in the exercise directory, so you need to /i createAgg.sql to actually create the function. We're going to go back to the results of this, but while the query is running, I'll quickly explain what this actually created. So it created 3 queue tables, one for the hourly, one for the daily, and one for the monthly aggregation. Then it also created the materialized views, each in different schemas, and it has one for the hourly, one for the daily, and one for the monthly. And on the hourly queue table, on the hourly materialized table, we have a trigger that inserts something into the daily queue. On the daily materialized table, we have something that inserts into the monthly queue. If we had a yearly overview, it would do the same for the monthly view. And then what's important, we have views, which actually are the ones you would use, that have the hourly view, the daily view, and the monthly view. And for the monthly view, we have to not only look at the materialized table of monthly plus the queue of monthly, but we also want to look at the pending changes in the daily or in the hourly tables, because we want to actually have the most recent value. So it should finish by now, I hope. Yes. You should have added timing. Yes. Do you have the query ready for group by in the Postgres repository, or do you want to copy it from the slides? I'll copy it. One before. Did you create this? Because there's no tables here. Oh, it's in PX, sorry. It's missing the schema. Oh yeah, okay. Yeah. Yeah, makes sense. Count star. No, count star is the table. Add the column. So in this case, we would have a table that lists the commits per day and shows the weekday of all over GitHub, and the query takes a rather short amount of time. And but that's not necessarily interesting. We want to be able to do something like per repository, because while it might be interesting for GitHub itself to see how many people are using GitHub, how many people are pushing to GitHub, to have a dashboard like the individual one we've seen for the Postgres repository in the beginning, or for the PG shard repository, you want to do something different. You want to show it per repository. So you can actually use this function that we presented earlier. No, well, that's not going to finish ever. Okay, can you show these slides? So what we want to do here is we don't just want to group by the type. We also want to say we want to group by the repository name, because we want to be able to query, say, the repository of name, for example, the Postgres repository. And for that, we need to look into the repository JSON-B object and look at the name field. And we want to use it as a string, not as a JSON-B object. That's why we use the double query. And otherwise, it looks pretty similar. We want to group by hour, day, month, and rename it. But this time, we don't actually want to look at the number of events. We want to actually look at the sum of the number of commits, because if you see one push event, for example, in GitHub, that can have 100 commits. And so we want to be able to see that. And luckily, the payload for pushed event or something has a field that says how many commits were made in that push, and also has distinct size, which is more useful, which says how many of these commits have not been seen in the repository before. Because otherwise, if you pushed a new branch to GitHub, it might contain all commits of the entire history, and you would see them again, which would make it pretty useless. But as you'll be able to see in a second, this one takes a long while to run, because now we don't just have one row in the hourly one per hour, we have one row per repository per event type. And obviously, that's a lot more rows. So just, if we assume it had already finished, we can see that for just the generally loaded, the hourly one grouped by type is 1.8 megabytes, by daily is 140 kilobytes, and monthly even fewer. But if you do it like by type and repository, you obviously have to deal with a lot more data, which is pretty much predefined, because we're not looking only at overall stats, we're looking at much more granular data. So one way to make things faster when doing pre-aggregation is to record less granular data, but that's, yeah, not that useful. So, and now we can finally reproduce the data for something like the GitHub graph that shows the number of commits per day. And for example, if we want to look at all the commits made in the Postgres repository, we say where repo name equals Postgres, and the type is a push event, and we look at the num commits field, which we defined here. The sum field is named num commits, and then this runs. But unfortunately, this here has to fill the entire queue, and it has to create these 600 megabytes of rolled up data. So this is going to take a while. And since it's going to take a while, we can drink some coffee. So we unfortunately are still waiting for the query here to return. And it seems my laptop is faster than EC2. But yeah. So one interesting detail to see here is we've written a... What did I do? Oh, cool. I didn't know that I can do this. You can use this kind of aggregated data to the most fine-grained or finer-grained data to build something less fine-grained that is more coarse, and you get very quick results if your overall data volume is still relatively small. For example, if you wanted a graph that shows, okay, the day-to-day activity in GitHub is visible, then we can do something like, okay, we want to extract the day from the datum, and then we want to see the type of event, and then how many how many events happened of that type, and so aggregate them together, and then say we only want to see push events, and then we want to group by the day and by the type, and we want to see the events ordered by the frequency. So that gives us, for example, to see how many commits over the entire time do happen on one individual day. And that's something you can often let you avoid doing more materialized views by saying I only do the materialized views that do the most necessary, the most expensive queries, and then do the rest of the queries on top of these materialized queries, because otherwise you end up with dozens or hundreds of materialized views, and that's obviously going to be expensive at some point, even if they are otherwise very fast to update. So for example, we can see here that Tuesdays, Wednesdays are the most productive ones. I'm actually surprised that Friday is more productive than Monday, but okay. Yeah. We can switch back. And then I think so far we can... So do you guys have any questions with what we talked about so far? Because I think this is a good point to stop for a second, like in the progress, not in the have another coffee break sense. And okay. So what we talked about so far was that, oh, I want actually this. That we have a way to do this incrementally for count star. We just insert plus ones and minus ones into the queue and use those to update the final value. The adaptation for sum, even if you haven't explicitly talked about it much, is pretty obvious. You just insert the actual value into the queue instead of the plus one, minus one, so that count star is basically just a special case over sum one. But the next more complicated, which is also pretty frequent in practice, is doing an average. But an average is, you can decompose an average to do a count star and a sum, and then compute the average that way. So that's pretty simple to do. After that, it starts to get a lot more dicey. One of the most frequent tasks when you do want to do aggregates is to compute the number of distinct types of events. For example, the number of distinct visitors. The number, and that's something that's really expensive to compute because you might have hundreds of millions of log entries per day, and you can't just do a count distinct over all of that data. So luckily there exist approximate solutions how to do that, and Marco will talk about how that's possible in a second. Another very common one is to I want the top 20 most frequent visited pages on my website or something like that. And that's, if you want to do that accurately, it's pretty expensive, but there's also, because you essentially need to sort the data, then group by, so that gets pretty expensive. What you can do instead, there's approximate solutions for that are much more efficiently. Top N is approximate top N. You can find some solutions. Yeah, there's even Postgres modules for it. So.
Thank you. So, as Anders mentioned, HyperLogLog is an approximation method for distinct counts because distinct counts are very expensive. And the main reason they're very expensive is when you're counting, like you kind of have to keep track of everything you've already counted because otherwise you don't know whether the new item you're counting is distinct. Compared to, you know, if you're just doing a count star, then it's just plus one, plus one, plus one. And so you need to keep a big list or table of items that you've counted. This is like not unbounded, basically, can take up any amount of memory. The lookups can be quite expensive. And especially if you're kind of in a partition table or a distributed table where the data is on multiple machines, this is especially impractical because then one machine doesn't know whether another machine has already counted an item. So HyperLogLog kind of approximates distinct counts. So it doesn't actually give you an accurate result, but it's pretty close. And what this lets you do is it lets you count faster. Not a lot faster, but a bit faster usually. Depends on the implementation. But mostly it has a fixed memory size. So there's a predetermined amount of memory that the HLL data structure will take up. And the HLL data structure can be incrementally updated with new items. So whenever you see a new item, you perform some function, or HLL can perform some function that updates the data structure to reflect the count. And one of the very nice properties of HLLs is that, or HyperLogLog, is that it supports unions across multiple HLL data structures. I'll show you what the HLL data structure looks like in a minute. But if you have two of them, so you've counted essentially two separate streams of data, counted the number of unique items in those streams of data, you could do a union between those two HLLs, and you would get the exact same thing as if you had counted it as one big stream of data into one HLL. And this can be especially useful if, well, one is if you have a more distributed database where you're counting here and counting there, you can put the results together. The other thing is if we're doing this method of taking a queue and merging it into a table, we can actually take the union of what's in the queue and merge it in with what's in the table. So HyperLogLog generally uses, always uses as a first step, a hashing algorithm, and the hash function will or should produce a uniformly distributed bit string. And this is like kind of important that it's more or less a random bit string that comes out of the hash function. So you can count items like, you know, any data type. There's actually a bunch of hashing functions available in the Postgres version of HLL. So let's say we want to count the number of unique repositories that have events on a particular day. This is kind of a statistic that's might be interesting to GitHub to see, you know, how much activity is there really on our system. Also, of course, interesting is number of unique visitors per day and things like that. Now, what HLL exploits is the fact that, or the way HLL works, is it has the reasoning that if you take a hash function, the result of a hash function, this bit string, and you see certain unlikely patterns occurring, that probably indicates that you've seen a lot of different items. So if you see a value, let's say, that starts with 5 zeros, well, the probability of starting with 5 zeros is like 1 over 2 times 1 over 2 times 1 over, it's 1 over 32 basically. So at that point you might say your best guess of the number of items you have seen before you get a pattern like that, a specific long pattern like that, is 32. It's a very bad guess. But as it turns out, what HyperLogLog shows, if you make a number of bad guesses together and you average them, you get a pretty reasonable guess. So HLL kind of divides the input. So every time it sees an item or it gets a different hash, it counts those in different buckets, basically. And all those buckets are making this horrible prediction of, like, if I see 5 zeros, then it's probably 32. If I see 6 zeros, it's probably 64. They're all making this horrible prediction. Then it averages them out, and it gets into, you can tune it to have less than 1% error, or even, yeah. So what does the data structure for HLL actually look like? So usually there's an add function where you take a hash and then you add it to an existing HLL data structure. So an HLL data structure contains a bunch of registers. So each register is just a number of bit. And the register will count for a particular stream. And the stream is determined by the first few bits of the hash values. So this, because it's a hash, kind of each item will kind of randomly be assigned a stream, but then, you know, when you see the same item again, it will go into the same stream. And it counts in the hash value the number of zeros from like this point. Okay, in this case, 4 leading zeros. And then it says in the bucket I, based on this, I take the maximum of what's already in there and the number of zeros I'm seeing now. And then in the end, I take more or less the average. I mean, there's some more complicated math behind it, but I more or less take the average across these buckets using the function, and I get a pretty reasonable estimate. It's kind of magical, but it works reasonably well. It doesn't give you precise estimates, but it does give you good estimates. So now, luckily, there is a very nice extension for Postgres that adds these HLL functions and also adds an HLL data type. So you can store this data structure in a table and incrementally update it. So every time, let's say you see a new item in your data table, you can do some counting in this HLL data structure, and then over time you'll get, you know, good approximate counts. So let's say again, on the machines that or the IPs that we gave you, the machines have HLL installed. You just need to do create extension HLL, and that will make the HLL functions available and will also make the HLL type available. So if you run this command, you can create a table. bit long name, but I've named it data daily uniques repos cached, where for each day we'll keep track of the number of unique repositories that had events. So HLL comes with a number of functions which are kind of important if you start using it. One is the HLL empty function, and this is how you always initialize an HLL value. This is like the 0. So when you start using HLL, you can insert into your table values. So we have a date, and then we put in an empty HLL. If we want to count an item, one thing we could do is we update the table, take the existing value in the HLL column, and add it with a new value that we want to count. And if you then do a select, and then there's this function HLL cardinality, like this is just a bit string, basically, with the bits that we saw before, these 1,000 registers. So to get an estimate for the distinct count, you call the HLL cardinality function on that table. Now, I have to say, in the Postgres HLL implementation, it's kind of smart when the distinct counts are very low. It doesn't do the magic. It just stores the hashes as a list in the data structure, such that it actually gets accurate counts. So this is not based on the probabilistic method. This is an actual accurate distinct count, which is obtained the way you would usually obtain a distinct count. But if we start adding more, at some point we'll reach the end of the registers, and at that point the Postgres HLL extension will switch to using the approximation approach. So, like, we have a number of queries for you that take forever, but it's mostly because, let's say, if you wanted to want to populate your data daily unique repos cache table with everything in the data table, then there is an HLL add aggregation function where you can take basically the HLL hash text of all the repo IDs in the data table, and then this produces an HLL data structure which counts all of those events, and it's grouped by date, so all the different repositories that had events on that particular day. So you might run this query. It takes a while, and partly just because distinct counts take a while. So I'll leave it here for a few seconds if you want to run it, and then I'll show you what happens if you actually try to do a regular distinct count. And the HLL package has pretty good documentation on the GitHub page. There's so it has examples of how to do, well, like examples like these, how to do analytics, and the different algorithms that it uses, and also some different trade-offs that you can make with HLL, which we'll also get back to. So if you were actually tried to run a regular count distinct query on the data table, this takes a very long time generally. I mean, there's a lot of different repositories that it needs to count. Fastest that it will run is maybe something like 10 minutes. So clearly, again, not a good way to implement a dashboard or something like that. But HLL allows us to do something smarter because it can be incrementally updated. So if we have the cache table, which will take some time to build, but after that we can just keep incrementally updating it, which will not cost much at all. Then we can just query that table, and this is pretty much similar to what we've seen before. So we can just select the date and the cardinality of the uniques from the table. We can put a filter on it, like I only want to see the last 7 days maybe. Again, you probably want to order by created date. And this gives us an estimate for the number of distinct repositories that we're seeing on that date. Now, you may have noticed they're not quite the same numbers because HLL gives an approximation. So do not expect it to give you the right number. Expect it to give you a close number. Of course, when you're kind of making a graph or something, then you wouldn't even see the difference if you were using HLL. So there's many applications where this is even though it's not accurate, it's very useful. And most of the time, you also don't care if you had 64,000 or 66,000 unique visitors on that day. It's more because they're pretty close together, really. Now, I don't recommend you to type this query, but this was a query to actually see what is the average error that we get across all these days if we compare the actual Postgres or SQL distinct count versus the HLL distinct count that we have in our cache table. And it's about 1.8% here. So on average, the values are going to be 1.8% off, some a bit more. Like this one, 1st of January was actually off a bit more, while the other ones are actually quite close. So it depends a bit. Sometimes you can see some larger errors. But actually, you can choose this yourself. The default settings will more or less give you this. But there are some settings that you can use when you define your table, particularly. By default, I think HLL uses 2048 registers. So it's basically 2 to the power 11. So you specify the power. And then the register width is the number of bits per register. So this is, remember, the registers are counting the number of 0 bytes. So if you have 5 bits, you can count up to 32 0 bits. And what this means is that there's a limitation to counting very high cardinalities. Like if you have sets that contain more than 4 billion items, then you might need to increase the register width, which will also significantly increase the memory. Also this one, of course, every time you increase this by 1, the amount of memory you take will double. And there's also this explicit threshold, which is like the point where the HLL extension switches from keeping an explicit list in its data structure to using approximation. And you could actually, so HLL tends to be a bit less accurate for low distinct counts. So if you have a lot of low distinct counts, maybe you want to increase this a bit so you get good accuracy for that. But that will also increase the memory a bit. So the way the accuracy is expected to work, and I mean, this is a sort of expected theoretical value. On average, this will be your relative error between what you see in HLL from HLL and what you see from a count distinct. The default value will get you up to about 2%, which is what we saw when we did the comparison query. Now, every step that we take to the right, every increase of log2m doubles the memory size. So This is 2, 4, 8, 16, 32 times larger than this. And you're thinking in terms of here it takes up about slightly over a kilobyte, and so you're going over on that side. It gets closer to a megabyte maybe. But you do get very accurate results at some point. Like you can get below 0.5% of expected relative error. Yes, I mean, so Anders brings up a good point where because we're storing the HLLs in these tables, like if you have an aggregation view that's quite large, like you have you know, a record for each combination of date type and repository, for example, and then you know you're counting the number of unique users in that repository. Like whenever you increase these settings, all of those datums, every row that contains an HLL column will become a lot bigger. So the storage size, like, you know, getting accuracy is nice, but you have to pay the price in memory usage and storage size. So be aware of that when you're when you're saying, oh, I want the most accurate results. You probably don't. So one of the really nice things about HLL is that you can take the union of two HLLs and they would be the same as if you had counted the items in one HLL. So here we are essentially just taking an empty HLL, adding 2 items to it, and we get some bits. And here we are, I'm saying this the wrong way around, am I? Here we're counting 2 items together. Which way around is it? Yeah, okay, so this one is 2 rows, and we're taking the union of the HLL for each row, and again, we get the same result, which is very useful, because since you can take the union of 2 materialized views, it's like adding 2 values. We can do the trick we had before. We haven't added like all the code for this, but you can create a view where you have a queue containing HLLs and a cache table containing HLLs, and then the outer query in the view takes the union of the HLLs in the cache table and the queue table. And you know, to make this work as an exercise, we'll actually leave the machines running for today. You also need the triggers and the flush function. One thing, it only works for insert because we cannot actually undo things in an HLL. We cannot easily remove, uncount things, or subtract one HLL from another. There are some techniques for doing that, but they are actually approximations. So they don't have this nice properties that they're, you know, that the union is the same as a single HLL that counts both. So all the things we discussed before apply equally well to to distinct counts using HLL. I want to take a quick look over here. It's finishing soon. That's great. Okay, we'll come back to that at the end of the presentation. We probably should have pre-built it, but this is more fun. So we wanted to say a few things about distributed tables as well. Are there any questions about HLL before I go on? All right, perfect. So there's actually a couple of ways of sharding tables in PostgreSQL. There's Postgres FTW, there's the PGShard extension for Postgres, there's CitusDB, and when you're sharding a table, I mean, there's many benefits to it. Also, especially also in terms of doing analytics. For example, you can do operations on the shards in parallel, and you can make the amount of work that you have to do when you ingest new data smaller by, for example, if you're using hash partitioning, you get many shards spread across a table, and you update each shard individually. But there are some restrictions that distributing a table creates. One of them is that, let's say you have a data table distributed over many machines and an aggregation table, then they have to be distributed by the same key. For example, we could distribute the table by repository. And it's also important that the aggregation is actually grouped by that key. So if we shard a table, we partition a table by repository, then one here will have the data for all the data items from a particular set of the repository, and we'll also have on the same machine the aggregates for that particular repository. So that works well. Then we can divide the work up between many machines. But if we want, let's say, an overall aggregation just by date, for example, not by the partition key, then we need to actually pull data from all those machines, and then it becomes a lot more expensive. The other partitioning scheme is commonly used is range partitioning, which is mostly used for time partition or for time series data, where new data keeps coming in, and every new block of data becomes a new shard, a new partition in your distributed table. And when you're combining it with aggregations, you can use the technique for incrementally updating materialized views on the latest shard. So you don't really actually divide the work of ingesting data up, but it still works. But if you want to do rollups over longer periods, over many shards, then again you need to get data from multiple machines. So you create, like the nice thing about distributed tables, you can divide up the work. So potentially you have a lot more capacity. You can do things in parallel, but there are some restrictions that come with it. So the other nice thing about distributed tables is, in some cases you might not need a lot of this because you can do parallel querying. So this is an example with CitusDB, which is a Postgres setup where you have many workers and then a single master. And then the data table on the master is actually stored in shards on the worker. And when you do a select on the data table, it will actually, the master will connect to the worker nodes and send out a bunch of selects for each shard in parallel. And this can work well. There's actually different approaches to doing this. You could query your raw data. If you have enough capacity, it might actually be fast, because, okay, maybe at the start we saw queries that take 2 minutes, but if we have, let's say, 120 cores available, they already go a lot faster. On the other hand, maybe you still have too much data. You can also query your aggregate. You can also store, for example, a fine-grained aggregation view and query that in parallel. So distributed tables give you some more things you can do. There are, again, some considerations also when you're making queries. Like if you have an aggregation query that has a group by on the partition column, that's a great situation, because then in a system like CitusDB, where it kind of has a relational algebra to determine how much of the work it can push down to the workers. Well, if there's a group by on the partition column of the table, then queries can be pushed down more or less directly to the shard. We're just doing a group by on the shard, and then at the end we're kind of more or less appending the results. Maybe there's some sorting we need to do and other post-processing, but it's very simple. But if we're doing a group by on columns other than the partition key, that means we have maybe some data from today here, some data from today on another machine. So then we need to do some aggregation, like we need to combine those results, where we need to aggregate those results. And then especially if you're using something like HLL, then you need to, you're doing your distinct counts on this machine, distinct counts on that machine, and then you need to pull them to the same place. And HLLs can be quite big, especially if you have many rows. And of course, you can also try to build a pre-aggregated view without group by. Then this can be pushed down directly. But then building a view, whether that's easy depends on, again, how you partition your data. Are you using hash partitioning, range partitioning, as we shown before? All right. This is now finished. It only took very many milliseconds. Yeah, that's interesting. So EC2 is not very fast, as it turns out. Yes. We also found out this last night that we built this AMI where we had this brilliant idea of putting the data in the AMI, and the AMI is the machine image, like that contains the operating system. And then we would just start a whole bunch of machines, and they'd all have the data preloaded. Well, as it turns out, the way Amazon starts these machines, and Andres feels I'm parted in this because I used to be at Amazon, but the way Amazon starts these machines is actually the data is still on S3. It's not actually in Elastic Block Store in their disk drives. So only when you read it do they fetch it from S3. So we saw like 7 megabytes per second read performance last night. So there's some of that going on, as we found out. Do you want to run some?
So in PG chart, you said there is a master node which coordinates. It's just like a zookeeper. So what if the master node goes down?
Well, the master node only contains a tiny bit of metadata, so you can set up a streaming replica, like a hot standby for the master. Like currently, we are sort of working towards making a PG shard masterless, where you have a bunch of nodes that contain the metadata. That's actually already kind of possible. So in that case, you don't really care too much if you lose a node.
So if let's say even if I create a replicated server for the master, and what if some of the metadata is missing? How would I rebuild the master? Because replication might miss something.
Sure. Yeah, I mean, you could use synchronous commit, or I mean, you could also, like, the metadata is so small, it's like you can do very, fast regular backups. Like if you miss something, like actually the metadata doesn't change very much, because it basically contains this shard is over there, this shard is over there, this shard is over there. That doesn't change much. The only thing that can change, so let's say suddenly is, oh, this shard has not received an insert while this shard has. But most of the time, like, the metadata is pretty static. So there's not a lot of, like, this is not a sort of highly transactional workload or workload with large number of transactions on the metadata. The metadata is static.
I'm really lost because let's say I'm sharding on a database,
Mm-hmm.
and each of my shard would go on a different node.
Yeah.
I have streams of clicks and impression data coming in.
Mm-hmm.
Let's say terabyte a day, and I'm sorry, like few gigabytes a day. So I'm adding shards every day
Mm-hmm.
or every hourly shard. So my metadata is changing and it's very volatile. So how would I? Because having one master is something.
Yeah, most users in production tend to set up a streaming replica for the master. Like, I mean, it's not an OLTP. You're not using it for OLTP workloads. So, Um,
question is, how do I rebuild if my master is corrupted by any reasons? Is there a way to recover?
yes, there's several ways. Like it can actually also recover just by inspecting what's on the workers, for example. We've actually written shell scripts that do that. Like, so that's possibly the easiest sort of or the most bulletproof way. Just looking at what's actually in the database. And to be clear, typically the shards are replicated across multiple workers. So like that part is quite fault tolerant. So if a worker fails, you don't have that problem. You had a question?
Memory? So you mean how large the
Yes. Well, no, we didn't put data into the cached table. What's the easiest way to see that? Like we can insert an item into the like one row into the table, I guess, and then.
or we can just
It's like in the end, you can see it here, of course. Like the daily unique repos cache table contains the HLL, so the size of those will be reflected in the size of the table. Hash text. In quotes. Data.
I'm going to limit this to subsets of the data because we don't want to wait. So there's a size function that returns the
Do you need the add?
No, I need to.
Add egg. Add underscore egg. Add underscore egg. And you want to remove the HLL empty. No, HLL underscore add underscore. Yeah. Just add egg. Add underscore egg. And then that, and then the group by. Or?
So now I'm computing the size. Can you skip words here?
With Alt.
Okay. So do you know the parameter for add arg which says the sizes?
It's a good question. Like.
That's default parents.
No, we'd have to check the docs.
No, it was wrong anyway. It was. I would have added here. I think it's actually this. Yes. So.
Okay, make it 12.
Yeah, that's what I'm trying to do. I'm failing.
So yeah, like once, so this is number of bytes. So once you get to the higher log2m values, which give you better accuracy, you're going to pay the price because now every row is going to contain a 15 kilobyte record. So taking up 2 pages. So especially, for example, you don't want to be updating those rows too much because it's going to generate a lot of big dead tuples. And here it's counting the number of distinct events. Like the hash is a kind of alias for HLL cardinality. Any other questions? Has anyone come up with something crazy to do with the EC2 instances yet?
As the query, the aggregation from earlier finished now, we can actually, hate this. We can actually now run on the queries on the table that shows us the number of commits per repository per day. So what I did here, I graphed the number of commits to the Postgres repository per day, and then said which also which weekday there is, so we can see on which day people work. Surprisingly enough, we start at Saturday and Sunday and then stop Monday. But yeah, so I think that's pretty much what you can do with what we built.
I guess it kind of completes the picture of having both fast queries that take under milliseconds and reasonably fast ingestion. It'll be a bit slower than before now because we now have a bunch of triggers on it, but it's still doing well over 1,000 rows per second, which is much better than, for example, what we had when we did the update trigger. Question? Say it again? Do you have any thoughts on this? That's good. Yeah, I think.
Is anybody using that in production right now? Not that I know of, but it seems trivial to provide an SQL buffer.
Yeah, we do, and we have actually a Citus data top and sort of approximation extension. Wow, this is good. Let's slow down a bit. Oh. Did we put an index? Yeah, you put indexes, right?
Yeah. We finished a bit quicker than we thought we would. Sorry for that, but we thought there would be a bit more questions, but either we were very boring or very good. I'm opting for the latter. Yeah.
If you have more questions,